So let us start with the first topic, which is the Hamiltonian. We have already introduced the Hamiltonian before. The Hamiltonian is defined as the product of the generalized momentum or the canonical momentum P multiply Q dot minus the Lagrangian. And symmetrically, the Lagrangian is defined as the same product P multiply Q dot minus the Hamiltonian. The most important here is the definition of the generalized momentum P, or the canonical momentum. It is partial L by partial Q dot. Of course, this is the first. This is an important equation. The second one is Q dot, which is partial H by partial P. Both, the second one, which is the green one, it follows from the first one by symmetry. Okay, because we are adopting here Legendre transformation. The first equation, it is partial H by partial Q equal negative partial L by partial Q. This is due to the fact that Q in the Legendre transformation is a passive variable, and partial derivative with respect to a passive variable is equal to both for both functions, but with a negative sign. And remembering that partial L by partial Q is equal to d by dt partial L by partial Q dot, and partial L by partial Q dot, as you can observe, is equal to the momentum. Hence, we get this equation, which is partial H by partial Q is equal to negative P dot, or P dot is equal to negative partial H by partial Q, which is the second equation of the Hamilton's equation, and the first one, which was Q dot equal partial H by partial Q. Okay, this couple is Hamilton's equations. Okay, and the last one to remember from last slide or last lecture is that the full derivative of the Hamiltonian with respect to time was equal to partial H by partial Q dot and partial H by partial P dot plus partial H by partial T. The first two terms cancel out due to what? Due to the pair of Hamilton's equation, and we get the important relation is that the full derivative of H with respect to time is equal to the partial derivative of the Lagrangian with respect to time. Hence, the Hamiltonian is conserved or is a constant if the Lagrangian does not depend explicitly on time, or if the Hamiltonian does not depend explicitly on time. So what? This last relation is very important, and it's very helpful to get an insight for the solution of a problem without integrating anything. As a practice, consider the problem of a harmonic oscillator, I have provided a maxima file here. The idea is so simple. You have got here a mass that's towed to a spring, and as we pull the mass to the right with the displacement x, it begins to oscillate. So it's a conservative system. We have got the kinetic energy, it is half the mass time x dot squared. We have got the potential energy here due to the spring, it is half kx squared. We can write the Lagrangian easily, it's equal to t minus v. However, I am doing here some non-dimensionalization, okay, based that the following is that the square root of m over k is the dimension of a characteristic time. Okay, so I am normalizing all time variables with respect to this characteristic time, and also I am defining an important quantity which is the amplitude of the displacement by a capital. So x or any length is normalized with respect to this amplitude. Okay. Finally, the Lagrangian is divided by k divided by a squared. If we go through this, the differential equation we are solving will be very simple, or the expression for the Lagrangian will be very simple. It will be x dot squared minus x squared over 2. That's all. Now we can go further and get the conjugate momentum. The conjugate momentum is partial L by partial x dot. You will find it as simply x dot. Okay. Then you can go to the definition and calculate the Hamiltonian. It is P, which is x dot, multiply Q dot, which is x dot also, minus the Lagrangian. As you can see, this is the Lagrangian. Okay. So this is the Hamiltonian. However, now we should pause and remember very important mistake. You cannot use the Lagrangian in this form because the Lagrangian is a function in P and Q. P is x dot and the Q here is x. So we need to substitute here x dot by P and x dot by P. You will find this step somewhere. Yes, we are substituting the dx by dt by the x dot solution 1. X dot solution 1 is here. P, okay, is equal to the x dot, or the differentiation of x with respect to time. Hence, we get this nice expression for the Hamiltonian. It's equal to x squared over 2 plus p squared over 2. And then we can substitute and get Hamilton's equation. However, this system of equation, which is x dot equal p and p dot equal negative x, it's not that easy for you to solve, especially if you are not familiar with the linear algebra. Okay. However, the Hamiltonian gives us a shortcut. The Hamiltonian tells us simply, based on the last conclusion, the following. Here, the time does not appear explicitly, okay, either in the Lagrangian or the Hamiltonian. Hence, the Hamiltonian is a constant, okay? It means that this expression, which is x squared over 2 plus p squared over 2, is a constant at any instant of time. So, for example, consider the initial condition x is equal to 1, okay, at t equals 0 and p equal to 0. Like we have just pulled the string and the mass and left it to oscillate. We will get that the Hamiltonian is equal to half, and it will be always equal to half. It will always equal half. So we can just request Maxima to plot the expression x squared plus p squared equal to half at any x and p, okay, and we will get this circle, as you could see. Fine, that's all. So this is very important, by the way, because it's giving us insight. So for example, consider this point at the upper right corner at which x is positive, and p also, remember that p is on the vertical axis and x is on the horizontal axis. So at this point x is positive and p is also positive, means that x will increase till we reach this maximum value. And consider this point at the fourth quadrant. You can find here that x is positive and p is negative, hence x should decrease, and the decrease will continue with us even in this third quadrant until we reach the minimum value of x. And then consider this one in the second quadrant, this point, x is negative and p is positive, so x will increase. So it's the oscillation, the oscillatory nature of the problem is very clear. This is one benefit. The second benefit is that, for example, considering that we are having the force is not just equal to kx but equal to k3x squared, okay, for this case Hamilton's equations cannot be solved. You cannot obtain a solution, okay. The system is not linear, it's non-linear. Still, you can find easily, or you can observe that the Hamiltonian again is a constant, okay. This is the Hamiltonian here at this case. It's equal to x squared over 2 x power 4 plus p squared over 2. Again, you can use any kind of initial conditions and request the plot. Fine. You will find it's a little bit different, okay. The maximum value of p here is not 1, okay, it's more than 1. However, the maximum value of x was 1. Why the momentum has increased? Because you have increased the potential energy by adding k3. It's not just k1x or k1x squared over 2, but now you are having another, it is x power 4 over 4 multiply k3, and we have introduced the ratio between k3 and k1 here in the form of kappa is equal to 2.75. Thank you very much.